Hello, everyone, and thank you for joining us today. My name is JC Hernandez, and I'm a tech transfer analyst at Johnson Space Center in Houston. I will be your host for this NASA Tech Transfer Program webinar on the Space Suit RoboGlove. Our presenter today is Emily McBrien. Emily is a design engineer who balances between hardware and soft substrates. She has designs in wearable robotics as well as wearables for robotics to protect against the extreme environments of space. She enjoys testing, design iteration, and taking ideas from concept to reality. Following Emily's presentation on the technologies, I'll be given a brief overview on how to license a NASA technology as an outside organization. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. So at this point, I'm going to turn it over to you, Emily.
Great. Thank you so much for that introduction. Can you hear me okay?
Sure can.
Wonderful. So the Space Suit RoboGlove had a predecessor, was the GMNASA RoboGlove, which was collaborated in 2007 between General Motors and NASA as a kind of a spin-off technology from our Robonaut 2 humanoid robotic work. And this was to aid in human scale, dexterous grasping and manipulation capabilities on humans directly. And so this was an idea of taking electronics on a hard robot that was used on that was designed to be used on the factory floor and directly apply it to a human body with a human worn glove. A lot of people think of like exomuscular systems like Iron Man. This was more of exoskeleton muscles like Iron Man has. The RoboGloves are more like an exomuscular system. It's a soft substrate that offload some of the stresses off of the muscles to open and close your hands, providing enhanced or assisted strength as well as endurance for repetitive tasks. Next slide, please. And then in 2015, this technology that was in the GMNASA RoboGlove got funded, granted to try to apply it directly to a spacesuit RoboGlove based off of the ILC Dover Phase 6 spacesuit gloves through some funding. And so the NASA Spacesuit RoboGlove was lightweight with different linear actuators than the NASA GM RoboGlove had, but same overall concept and design. It had all the electronics and microprocessor was located on the form of the glove, still fed off of the tendon-driven system that existed in Robonaut 2 or R2. And the big difference between like the first generation, the NASA GM RoboGlove and this first generation of the spacesuit RoboGlove was a difference in sensors. We use localized tactile sensors and force-sensitive resistors to help drive that technology forward. Next slide. And then the second gen NASA Spacesuit RoboGlove really kind of enhanced on the first generation, but had more development and testing, a lot of testing actually, and more of a focus on how is this usable for our space and NASA exploration missions, and with focus on durability, the how quick the glove can be installed, not installed, but put on and kind of programmed to be useful. We had different sets of calibration cycles to reduce hand injury to astronauts, and then make it more durable and make it more sensitive in the right areas so that it can be put on and immediately used if possible. Next slide. So the goals and overview, the first generation actuators were directly transplanted into the second generation. We had a series of test results from the first generation in FY15 to show some of the peak performances of these actuators. We wanted to you utilize those actuators performances even more. And so we did some redesign on the actuators to make it more simpler, make maintenance more simple, and we did a lot of work. And by we, I mainly mean me, on making wear in the tendons, make the tendons last longer. Next slide. A big difference between the first generation and the second was improved sensing and controls and the interface with the electronics. And these gloves, and I feel this is true with all robotics, is that they're only as usable as they can detect the environment around them. And so that really required us to enhance the sensors on the glove. So we adapted sensors on the finger position that would help to, enable the controller to incrementally close the glove as opposed to like all closed, all open. And utilize additional sensors other than just the force sensitive resistors to provide better feedback for the user and to get that intermittent control. And so this kind of gave us the ability to have power steering mode for the users. And with the power steering, like once you put on a spacesuit glove and it is pressurized, it does take a certain amount of pressure or strength just to move within the glove because you're fighting that pressure within the gloves, like you're fighting it's like a spring constant just to move your fingers. And so it already takes work just to move your fingers within it. And so this power steering mode, you start to move your hands and the glove, it doesn't take over, but it immediately starts to assist you and gives you that additional control where before, if you just move a little bit, it took X amount of force. Now it takes a lot less force because the robotic actuators are directly providing that assistance. With that increased assistance through the power steering, we also had to improve the overall integration of the hardware into the soft goods gloves. And we did that mainly by focusing on the tendon and making sure we had a good interface between the user's fingers where that tendon pulse force diagram or force system was directly applied to the user's finger. So we enhanced that for better comfort. Electronics and avionics got an improved upgrade to deal with the additional sensors and needed for the computation for higher computational power, and developed a system appropriate for this rapid software and firmware iteration to make it easier for developmental testing and just trying to get again that calibration of you put on the gloves, what is the time spent between you put on the gloves and you're ready to have it help you. And with the improvements to the avionics and the software, we took that from several, like a 10-minute protocol down to like a 10-second protocol in terms of like rapid ready to go firmware. Next slide. So I think that this was a very successful 2 years of iteration and design. We did successfully manage to iterate this hardware into a pair of phase 6 gloves. So two, we had a left and a right. We had a design improvements to the actuators and the overall control system with every chance that we had. So even like, NASA GM RoboGlove, there was a big improvement to the first generation and then a big improvement onto the second generation in terms of feasibility and performance. We developed some novel control mode analogous to the power steering feature that was found in automobiles. And the system ultimately showed that we could mitigate the effects of a pressurized glove on a finger joint torques in real time. And the second generation RoboGlove does represent the latest iteration of this technology and may be known as just Space Suit RoboGlove or SSRG for the remaining of conversations. Next slide. So yeah, overall for overview for operations, the glove itself does not actuate the thumb. The design team decided to focus on more of like the four fingers for a myriad of reasons. Mainly the thumb is already the strongest joint, and so we can get the best bang for our buck by focusing on the weaker joints, especially on that extension. A lot of people have a good grip for flexion, not the best grip for extension. It's just not where a lot of our power lies. So we wanted to utilize, find our weakest and make it stronger. The Space Suit RoboGlove also retains the ability to operate like a conventional spacesuit while the actuators are unpowered. So we did a series of testing without the power going to the glove as well as with it, and just to show that we did not make the performance of the Phase 6 glove worse by adding our hardware in, and we did not. You could still detect, so the device could detect fine finger movements of the user as well as interactions with objects. So between our different sensors that we integrated into the glove, the controller can command the actuators to drive in specific cases that was most helpful for the user or wearer. And yeah, the actuators are located down on the forearm, which is very similar to how our own arms work. The bulk of our muscles are located in the forearms, and then we have a series of tendons that actually go up and attach to the bones in our fingers. And these actuators are designed the same way. We utilize the forearm since you can put more mass there, more weight there without it being a encumbrance to your dexterity. And then we have a series of synthetic tendons that route through the glove and attach the medial phalanges of the fingers to assist in the user to close their hand. Next slide. So this is an overview of the mechanical actuator system. We have 3 actuators and a controller that's all located on like the forearm of the user, and the Bowden cables is what delivers the movement of those tendons safely without pinch points and additional wears from the actuators up through the arm, through the palm, and into that attachment to the medial phalange. So linear actuators, the Bowden cable systems, the palm bar is something that already existed within the Space Suit gloves itself, and we utilized that to help complete our force diagram so that we can have this whole system like on a bench and move these actuators without having to um, ground it in any way. So basically, this is a closed system between the actuator, the Bowden cables, and the palm bar, with some reactant forces on the tendons to actually pull your fingers down. But like there's no additional torques that the user has to ground. This is a fully closed mechanical system. And then the finger saddles is what actually comfortably connects the tendons to the user's medial phalange. We control 4 fingers. We only have 3 actuators. The secondary fingers, your pinky and your ring finger, are coupled all in actuator 3. And that's also true with our own biology. We have a lot of trouble moving one finger without the other because we do have natural coupling of those 2 fingers already. So we utilized, grouped them together under the same actuator to decrease the amount of complexity in the system and overall weight that would be on the user's forearm. Next question. Oh, next slide. Sorry. Just go into a little bit more detail about this, about the mechanical actuator system. We have to move a finger with the actuator pulls a tendon that routes through the Bowden cable system, ultimately transferring a mechanical pulling force to the user's finger. And it goes to the Bowden cable similar to how the brakes work on a bicycle. So there's a series of inner cables relative motion to the outer cables, so that you can, like, on a bicycle, you can rotate and it still doesn't impede on that linear motion of the brake inside to move forward and back. So tendon operates with that same design. This Bowden cable is a spring conduit that is very strong in the axial direction while still remaining flexible in the other direction. So it doesn't impede on the user's wrist movement at all. We place them also strategically so that you can have full use of your wrist flexion and extension without these conduits getting in the way. Yeah, next slide. Excellent. The actuators themselves are comprised of a brushless DC motor with a planetary gearbox and a ball screw. All of that, turns that rotational movement into a linear pull. And on these actuators, we have a stroke of 3.15 inches. The stroke of the actuator, or how much that linear ball carriage can move, directly translates into the amount of movement that you would get in your hands. So we tried to optimize and get a good length for this without being too long, because of course, as you get longer, you have to somehow still fit on the user's forearm. And 3.15 inches was a good compromise. We found that even people with the largest hands could utilize the 3.15 inches of stroke and get the performance that we wanted out of it. That being said, the same actuators exist on someone with say, a smaller glove. So we just don't utilize the full 3.15 inches for smaller glove sizes, but the actuators themselves are the same. So no need for custom sizing. And the housing is constructed out of aluminum 7075. This provides the linear alignment to make sure we're getting that full strength out of that motor. It's also a shield against debris, and there's also some built-in hand hard stops and thermal mass included into it. So all the aspects of this are designed to provide good mechanical alignment, thermal mass, as well as make it easy to kind of construct and reliable throughout the life of the actuator. Next slide. Some design improvements or just differences between the Space Suit RoboGlove and the original NASA GM RoboGlove is we wanted to utilize higher force outputs with increased efficiency, higher thermal mass with improved reliability, and also ease of maintenance. So this is a good comparison. We went from 113 newtons of force up to 163. And we really wanted to utilize a higher force because the working conditions within the spacesuit glove, it being pressurized, for example, just required that much more force to get over before you had the chance to actually helping the user actually hold tools and perform specific tasks. We did take a hit to speed. We went from 90 millimeters per second. We went from 100 to 90. Overall, we have larger mass, but the larger mass increase was mainly for a higher thermal mass that we added to help keep the thermal system a little bit more stable, especially given the environment of being within a vacuum. We couldn't rely on some of your more conventional convection ways of cooling a system. And we went to a higher higher motor power from 12 watts to 60. And again, that tendon travel was a big benefit. We were limited to just 2.52 inches before. And remember that tendon travel is directly related to how much you can close your hand. So someone with a larger hand wasn't able to get as much performance out of the original, NASA GM RoboGlove actuators, whereas with the spacesuit RoboGlove ones going up to 3.15, we extended the capability of our user hand sizes. Next slide, please. Overview of how this whole fits into the system of the spacesuit glove itself. The spacesuit RoboGlove drivetrain are split between layers with the motor, controller, and one side of the boat and cable. And then on the other side, we have the other side of the palm bar, the boat and cables, and the saddle. So your typical spacesuit glove, you've got your human, the bladder, which is your bubble, sorry, the bladder is the thing that protects you and has like your life support system ends at the bladder. So basically live in a big balloon. And the restraint goes next. And this provides like the structural integrity of your glove to keep its shape. Otherwise, that balloon would just keep inflating out to balloon size. And then the whole thing is covered with a TMG, or a thermal micrometeoroid garment, to provide durability as well as protect you from the hazards of the space environment from radiation, thermal, and micrometeoroid, and overall abrasion. Now, for the spacesuit RoboGlove, what we did is we put a series of hardware in between the restraint and the TMG with our own little hardware layer. And then we also mounted like the palm bar, the boating cables, and the saddle directly into the restraint itself. Next slide. So with the restraint layer, this is one of the more complicated integration of hardware to the soft goods. All the components are integrated into the restraint layer, while ensuring that the restraint layer can still do its job and all of our components can still fulfill their role. So a lot of the design of well, I'll say every stitch on the restraint layer is highly engineered and has been engineered for the last 50, 60 years. So there's a lot of information known about the restraint layer. And so we came in and we had some limited capability of where we can put things, but working very diligently with a lot of iterations. This is how we've placed things. We've got the palm bars going over on the sides of the palms, side of the wrists, and then they cross into the palm area, connect to that palm bar right at the metacarpal phalange on your hand, and then the tendons themselves route up in the dorsal side of your fingers, and then attach in the finger saddles that go around. That's the boating cable system. On the back side of the hand, we have mounted a series of string potentiometers as our increased sensor suite for the second generation of Space Suit RoboGlove onto the back part of the hands to get that measured position. That's how we really get that power steering effect. It was using the feedback from the string potentiometers. Next slide. The tendons and the saddles themselves, this is again like the thing that integrates directly with your finger through the metacarpal joint and goes down and this is the thing that translates that linear force from the linear actuator to your hand. So this is the interface between robotic and human. The tendons themselves are made out of a selection of Vectran and Teflon braid that we have a lot of experience here at NASA on Robonaut 2, RoboGlove, as well as Valkyrie. And each of these tendons uses a single eye Brummel to interface between the actuator and the tendon, and then a triple Brummel pigtail to anchor between to anchor to the saddles and onto to that medial phalange on the human's hands. And all this was designed in-house. I think I spent 6 months of my life on these 2 images. So next slide. The position sensor integration, this is what really was a big difference between generation 1 and generation 2 of the Space Suit RoboGlove. But we have it on the posterior position of the hand, measuring the distal phalange relative to the palm for the index, middle, and ring. And all of this, we have a control system that utilizes these sensors to calculate your actuator position during operations. I'm just gonna, if you guys want to look at my video instead of the pictures for just a moment, but basically it measures the position of the distal part of your finger here to your palm. So if you think of it like how much am I moving my fingers going from a completely open position to a completely closed position. Say that was 2.8 inches for me if I like pulled this string on the back of my hand. So that 2.8 inches for me to move my index finger from totally open to totally closed would be measured within that string potentiometer, and that would be directly correlated to the calibration sequence that we did of that stroke on the linear actuator that says, hey, you got 3.15 inches, totally open to totally closed. For Emily's specific index finger, totally open to totally closed is now 2.8, and it calibrates that position between my own custom finger and the linear actuators on the Space Suit RoboGlove itself in order to provide that immediate assistance for the user. Next slide. This just goes into where all the hardware is mounted. Again, we really focused on not having impact to the overall system, so that on the outside it would still look like your regular spacesuit glove TMG, and we have all of our hardware mounted on like this hardware layer constructed out of soft goods. And we have a few things measured inside, like the TMG itself. We put in some force-sensitive resistors embedded into the distal and medial phalanges of the fingers. So a TMG has like this silica coating on the front of it to give the user some good grip, good friction. We have sensors actually embedded within those. So again, I think very little impact to the overall glove and look, but we added capability where we could without much of a difference or impact. And then the wires pass through the fabric of the TMG and route to the avionics layer. There's actually some heaters that are an option for regular spacesuit operation. So we already had like a wire path that we could utilize. So we tried to integrate as seamlessly as we could to their system. Next slide. And the user interface, we've got a series of different control modes that can be customized to each actuator and sensors to better complete a task. The main modes for when we were testing the prototype were just idle, calibration, power steering, and power steering with grasp strength augmentation. And we had an overall switch that was embedded into like the cuff layer that the user can switch between. We do have the capability of providing up to 9 different modes, and I can go through a little bit of the different modes. Like idle was just you don't want to use it. You want to use your bare hands. That's fine. Calibration, which is what I had mentioned before. That's that calibration of it takes 2.8 inches for Emily to close her index finger from fully open to fully closed. That would then be calibrated to that linear stroke of the actuator, so that as I move my finger closed, the actuator would be correlated with that positioning. That provides that power steering. And the power steering with grasp assist utilized the force sensitive resistors that we had built into the TMG of the glove, so that if I got my power steering here, and if I actually grab hold of an object with enough strength, that would trigger an additional grasp strength augmentation. Next slide. Avionics system, we used an Athena microcontroller with a multi-axis motor controller. This was a custom in-house for NASA's Valkyrie humanoid robot to control her fingers and wrist actuators. This has 4 slots to attach peripheral boards, also known as tiles, so that the entire motor controller itself is a little bit modular. You can add tiles depending on what hardware you have. In this case, we have 3 tiles for control our actuators, and then a sensor tile as well. But if you had a different system, you can just kind of customize it with the tiles that interface to the Athena motor controller. Next slide. A little bit more on the sensor tile, since this was really what, again, the robot's only as good as the sensors that can read the environment around it. So the dedicated sensor tile, we made it configurable for 4 groups, for 4 individual interface circuits, so 16 channels of different sensors that we could utilize. And this is the part where it got a little bit warm, depending on that high processing power, to process all of that data as quickly as we could. So we did utilize a fan and a heat sink to help reject heat from the system during our testing, and that's also why the thermal mass of the system got a little bit larger. Next slide. Overall control system, I've got more of a mechanical brain, so I like my visuals of this is how you calibrate it. This is actually how you calibrate it through this control system with our main processing, FPGA program fields, and just using a separate code for the motor controller processors. Each one has a different set of scripts and processes that are shared within the DDR memory and peripheral bus access. But it's all correlation of correlating those glove sensor positions to that motor positions, avoiding the positive feedback control of, motors moving. Doesn't that eventually cause your finger to move? A lot of balance there within that position control to make sure that the glove was measuring your user's intent to move as opposed to creating the intent to move itself. All that goes into the control system. Next slide. And data collection, the FPGA communicates with the external devices through something called RoboNet, which is our communication protocol that we use on all of our robots here for RoboNet 2 and Valkyrie, or all of our Destrix humanoid robotics. And the processors on the Athena has access to the central data repository that will store all of the operations and parameters for the Athena processors. So RoboNet automatically synchronizes the data between the Athena and the laptop. It's got a graphing tool so that we can look at display real time for system monitoring, and use it to do manual adjustments of the controller parameter. And so like when we were doing testing with the humans in the loop, we had our controller here. We could see all the direct live feedback from all of the actuators, whether it be temperature, torque, current, not torque, calculated torque based off of current and voltage of the actuators as they were working, as well as sensor feedback. So if it, force sensitive resistors, we could see that force, live, and the string potentiometers live. And while connected, we were able to make the glove, more or less sensitive, depending on the user's feedback, and that all kind of played into the extensive testing that we performed to evaluate this device. Next slide. So for startup procedures, and this got, from a long 10-minute thing, we tried to cut it down as much as possible. But after the master computer was connected and ready for communication, we went through overall tuning parameters that's set in the master computer, set up the data plotting tools. Once, that's all on the test director side of things. When you put on the gloves and actually power them up, we go through an actuator homing system with the string potentiometers. That is going through your hands are fully open to your hands are fully closed. And it was just as simple as that: hands open, hands closed, with the use of the actuators, so that you would be relaxed as it did that, and that would calibrate the position of those linear actuator stroke lengths to the length, stroke of your own fingers, and that was it from the user's point of view. We did have a kind of a larger startup procedure where you could additionally calibrate, again, that sensitivity of the glove to be more or less sensitive depending on how what the user desired. But ultimately that power steering came from that calibration exercise. Next slide. Yeah, safety and fault identification. This was a very important thing, especially since we were adding on to spacesuit operations. But we had a series of temperature sensors, and if out of bounds, a fault would be triggered. Just disable the glove. Electric shock. Again, nothing was exposed to the user's hands, or even within close proximity to the glove's bladder, which meant we had very low impact on the life support system of the astronaut either. The entire glove was fully back drivable with easy to back drive, so that if the system had to be saved in any way, it would go into a fault which just said power off, and then once it was powered off, the whole system could be easily back drivable, meaning you can, if the system got shut down in a closed position, you can just open your hands, because the efficiency of those actuators are so high, you can easily back drive them and get it to whatever position you need to. A lot of times we would just open them completely and then go about your business, since we had low impact on the performance of the gloves in the off position. And then the supervisor, or the person on the computer can examine that fault data through the tools and try to reset or restore the powered assistant glove as depending on the fault. Next slide. So the second generation Space Suit RoboGlove represents refined electromechanical system components, soft goods integration, and a control system. We had a variety of test subjects that were executed with the high performance glove evaluation test protocol using the Space Suit RoboGlove. This HPEG test protocol included a dexterous task like picking up these U-bolts and turning 90 degrees, how quickly you can do that, tactile feedback, strength, as well as fatigue and general tasks, using standard tools and mimicking spacewalks through handling of walking on handrails. And we tested pretty well on that against the other gloves that being under consideration. We kept the team. We kept everything on a wiki site with code repositories and a CAD library to preserve all the detailed engineering data. So we have that all packaged, ready to go, nice and refined, ready to open it up whenever the opportunity presents itself. And for commercial applications, I see this in a wide range of areas, from medical rehabilitation and prosthetics, constructions, manufacturing, anything that requires, like anything that has, like, you have to do normal tasks but wear heavy gloves to protect the user. I think this technology could be a good application for. And the design intent is to provide the user with enhanced ability to perform human scale work with considerations for speed, power, durability, dexterity, and ease of operations to whatever your tasks may be. Next slide.
Thank you, Emily, so much for that excellent presentation. Really appreciate that. And once again, we really appreciate you taking the time to be with us. Thank you so much, Emily. We definitely appreciate your time and all the great energy you put into this technology. I'm JC Hernandez. You guys have a great day.